So let's kind of go through the solutions here to this handout, then we'll take some questions after that, and then move on to the next topic here. So number one is x squared plus 2x minus 15 plus 2 over x plus 2. Yes. Not a ton, because I still need it to be able to see the whole thing, and some of these problems get kind of long. That's probably about as good as I can do. It's also posted to Power School, though, and I'm reading it aloud. So we'll do the best we can, right? Yep. If you find the assignment on the calendar, it's attached with the assignment. Maybe hitting the lights would help, though, and you're welcome to do that. All right. Number two is x squared plus x minus 12. Notice in that one you had a remainder 0, so that's it. There's no, you don't have to do plus the remainder over the divisor because we had a 0 remainder, right? Number 3, we get 2x to the 4th minus 19x cubed plus 13x squared plus 139x plus 105. Again, with a remainder 0, so that's it. We don't have to write anything after our quotient. And then the last problem on the first page is just x minus 5. So if you notice there, the way I set that last problem up is I just did 3 successive or synthetic divisions, where I just used the answer from the previous synthetic division as the input for the next one. It was pretty quick for a problem that looked kind of complicated there, right? On the next page, number 5 is 2x minus 3 times 4x squared plus 6x plus 9. Number 6 is x squared minus 5 times x squared plus 2. Number 7 is x plus 2 times x squared minus 7. Number 8 is x minus 2 times x plus 2 times x squared plus 4. Number 9 is x cubed minus 7 times x cubed plus 5. Number 10, 3x plus 4 times x minus 3 times x plus 3. And then if we go up to number 11, this is a long one. Number 11 is x minus 2. I'm sorry. It is 2x squared plus 5 times x minus 1 times x plus 1. Number 12 is x minus 2 times x squared plus 2x plus 4 times x plus 2 times x squared minus 2x plus 4. Thirteen is 2x plus 3 times x minus 2 times x plus 2. 14 is 2x minus 1 times 4x squared plus 2x plus 1 times x minus 2 times x squared plus 2x plus 4. And then lastly, number 15 is x to the 4th plus 16 times x squared plus 4 times x plus 2 times x minus 2. Questions from you guys? Madison. Number 3. Okay. So we should note that if I look at this problem to decide whether I want to do synthetic division or long division, I need to look at the divisor. The divisor here is 3x plus 5. And although the degree on that divisor is 1, its leading coefficient is not 1. So I can't use synthetic division as it's currently written. So we'll set this up as a long division problem. So the divisor goes on the outside, and then the dividend goes underneath our division bar. So that's our initial setup. Once we have this, we're going to ask ourselves, what times 3x gives us 6x to the 5th? So it definitely has a coefficient of 2. What is going on? Because 3 times 2 is going to give us 6. And x to the 4th times x gives us x to the 5th. So 2x to the 4th is the correct answer there. And then I'm going to multiply that to both terms of my divisor. So that'll give me 6x to the 5th plus 10x to the 4th. And then I'll subtract down. So 6x to the 5th minus 6x to the 5th is 0. And then negative 47x to the 4th minus 10x to the 4th is negative 57x to the 4th. And then I'll bring my next term down and re-ask the same question. What times 3x gives me negative 57x to the 4th? Well, negative 57 divided by 3 is negative 19. And then I know that x to the 3rd times x gives me x to the 4th, so I have 19x to the 3rd. And then I'll multiply that to each term of my divisor. Oops. Let's Try again there. So negative 57x to the fourth minus a negative 57x to the fourth gives me 0. Negative 56x to the third minus a negative 95x to the third is the same as just like 56 or negative 56 plus 95. So that's going to give me 39x cubed. And I'll bring the next term down. And ask the same question over again. So what times 3x gives me 39x cubed? Well, that's going to be 13x squared. And then I multiply that to both terms of my divisor. And subtract down. 39x cubed minus 39x cubed is 0. And then 482x squared minus 65x squared is 417x squared. We'll bring the next one down. So then I'll ask myself, what times 3x gives me 417x squared? Jeepers creepers. 417 divided by 3 is 139. And then I know x times x is x squared. So when I multiply that to both terms of the divisor, I get 417x squared plus 695x. Then I subtract down. 1010 minus 695 is 315. Then I'll bring my last term down. So this is my last step. And then I'll ask myself, what times 3x gives me 315x? Well, that's positive 105. If I multiply that to both terms of my divisor, I get 315x plus 525. And when I subtract down, I get 0. So my answer here is just that. Madison, are you okay with what I did there? Okay. Did anybody figure out a way to use synthetic division to do this problem? So we can do some modification to this and still use synthetic division on this since it's a degree 1 polynomial. Here's the trick. I need to figure out a way to rewrite 3x plus 5 so that it has a leading coefficient of 1. Well, I can do that by just factoring a 3, greatest common factor of 3, off of that divisor. Everybody see how I did that? Now if I look, if I divide by this, that's degree 1 with leading coefficient 1. So I can use synthetic division to divide with that. So let's just see how that would work out. So on the outside, I have the negative 5/3. I have 6, negative 47, negative 56, 482, 1010, and 525. Everybody so far so good? You see the trick that I used to make this into a synthetic division problem? There's still going to be some little adjustment I have to do from taking that 3 out. But that doesn't, I don't need to worry about that until the very end. I can do the division. So I bring the 6 down, and then negative 5/3 times 6 would be like negative 30 over 3, which is just negative 10. If I add down, that's negative 57. And then if I multiply negative 5/3 by negative 57, I get, let's see, what's that? It's positive 95. And when I add down, I get 39. And then negative 5/3 times 39 is negative 65. And I add down, I get 417. And I multiply that by negative 5/3, and I get negative 695. And I add down, and I get 315. And I multiply that by negative 5/3, and I get negative 525, which gives me a remainder 0. Everybody okay with what I did there? Now, you probably would have wanted to use your calculator to do the fraction multiplications and reducings. Like, unlikely any of us were going to try to do that with our heads, and that's fine. Now, we've only divided by part of our divisor, right? Notice that we didn't divide by 3 yet at all. Everybody sees that? So how am I going to fix that? So I still need to divide by 3, right? So the workaround is I can just divide each of these guys by 3. And if I look now, those match, right? So if you are asked to divide one of these problems, and the leading coefficient isn't 1, you can't use synthetic division as it's set up. But if you're clever, you can do what we just did there, factor out the leading coefficient, do the synthetic division, and then divide your answer by that leading coefficient. And you can still use the synthetic division to do that. But you have to kind of be sneaky about it, like we were there. But that's a nice little trick, right? Because that problem, as a long division problem, was kind of a pain, right? I made this problem for this specific reason, so we could go about and talk about this little trick. And usually students really fail to appreciate it until they've done a long division problem that's pretty grueling, to go, oh, yes, okay then. That is a good trick to remember. Because if you compare the two sets of steps, which one would you rather do? Yeah, we'd rather do that synthetic division step. Now it's unlikely that any of us would have come up with that trick on our own, right? That was pretty sneaky, to just do the division in 2 steps. Like, we'll divide where the leading coefficient is 1, and then divide that leading coefficient, right? Which is what we did. But we can do that, right? There's nothing wrong with doing it, right? If I divide something by 6, I could divide that number by 2, get an answer, and then divide that number by 3. It's still doing the same thing. Tom?
You always say we only do that, or no?
Mm-hmm.
No.
It may get really inconvenient. Like here, you notice when I did the multiplication, I always got an integer, like a whole number. That may not happen. You might get fractions, and then it gets to be very grueling, like just tedious. Like, not that it's any harder than this problem was. It's just like a pain in the butt to have to deal with all the fractions. But the long division, you're going to have fractions all over the place too, so it's like equally a pain. So it could get ugly, is my warning to you, but it would have been ugly the other way still also. Madison, are you happy with what we did there for 3? So we beat that one pretty good into the ground, right? We did that a couple of different ways. But hopefully you feel a bit better about that now, right? Who else wants to ask about something from this assignment? Olivia? 10? Sure. Okay, so on these factoring problems, the first thing we need to do is to look at the number of terms, because that's going to give us some instruction about what kind of factoring do I want to try to do here. So in number 10, how many terms do we have? We have 4, right? So if this is factorable, we're going to have to use grouping to factor it. When we do a factor by grouping problem, what's the one thing that I have to really remember? It's that the symbol in between the two groups has to be a plus sign. So notice in this problem, the symbol between the two groups would be subtraction. It's the easy fix is I have to just write that as plus a negative, and I got it taken care of. I'm guessing, Olivia, that was the issue. I put this problem on there specifically so that we could remember this. Every class is asked about it. So if you missed writing it as plus a negative, you're probably in the majority. But now that you've seen it and you've been reminded about it, try not to forget for the next time. Or if you catch it not working out, go back and check that, because it's a likely place to make a mistake. Okay. First group, we have a greatest common factor of x squared. That's going to leave me with 3x plus 4. In the second group, we have a greatest common factor of -9. That'll also leave me with 3x plus 4. If I look at the whole thing in totality, I have a greatest common factor. It's 3x plus 4. And when I factor that off, I'm left with x squared minus 9. But I'm not done here. I have to check each of those factors to see if they can factor. Now, 3x plus 4 can't factor because it's a degree 1. No degree 1 polynomials ever can factor. Well, anything more than like a coefficient. Like you can take, I could take a 3 out of that or something, but, like that's not interesting. The x squared minus 9, though, can factor, right? Should be easy to look at that and notice that it's a difference of 2 squares. That you have x squared minus 3 squared. So when we apply the difference of 2 squares, we have x minus 3 times x plus 3. And that would be our final answer. Olivia, you happy with that? Okay. All right. Who's next with questions? Henry.
Can you number 14, please?
Sure. Okay. So first thing we're going to do, looking at the number of terms. How many terms does this polynomial have? 3. So if it's factorable, I'm going to need to make sure it's in the quadratic form, right? So let's look at this. Is this in the quadratic form? I have a degree 6. And then a degree 3, and then a degree 0. Yes, right? Because the leading coefficient, or the leading term's degree is twice the middle term's degree. 6 is twice 3, and the last term is degree 0. So this is in the quadratic form. So I'm going to go ahead and make my substitution. I'm going to set y to equal x cubed. Remember, I just set y to whatever the variable on the middle term is. And when I make that substitution then, I get 8y squared minus 65y plus 8. So I have something now that's distinctly quadratic. So if I can factor this quadratic, I can use my factoring techniques from chapter 3. So notice here, this quadratic has a leading coefficient that's not 1. So I'm going to have to do that longer factoring technique that involves grouping. So I need to find the two numbers that multiply to give me 8 times 8, and then add to give me negative 65. Hopefully it's easy to see that those two numbers would be negative 1 and negative 64. So I use those two numbers now to rewrite the negative 65y as negative 64y plus a negative 1y plus 8, and make my two groups. From the first group, we can take out an 8y, leaving me with y minus 8. And from the second group, I can take out a negative 1, leaving me with y minus 8. Now, if I look at the thing in totality, I notice that there's still a greatest common factor. Each term contains a y minus 8. When I factor that off, I'm left with 8y minus 1. But I'm not done here, because I wanted to factor over x, not over y. So let's go ahead and substitute back in our x's. And now I need to check to see if either of those factors can be factored. I notice that each of them is a difference of 2 cubes. X cubed minus 8 is x cubed minus 2 cubed. And 8x cubed is 2x cubed minus 1 cubed. Right? Everybody can see that? So to factor the first factor, I'm going to have a minus b times a squared plus a times b plus b squared. And to factor the second factor, I'm going to have a minus b times a squared. 2x squared is 2x times 2x, or 4x squared, plus 2x times 1 plus 1 squared. Okay with that, Henry?
Yeah.
Okay. So again, remembering that long factoring process was kind of the key there. If you didn't get or didn't recognize that, that was the catch on that one. If you got that far, you probably got to the finish. Okay. Others. Okay. Well, today then, we're going to move a little bit forward, but just a tiny bit forward, to talk about solving polynomials. So, to do this, let's just look at these two that we factored as examples. So let's say that for number 10, we were asked to solve for x, and I just have that this is equal to 0. Okay? To solve any polynomial, the first step is to make sure that it equals 0. So we don't have anything to do here. Now what I'm going to do is I'm going to factor this polynomial just like I've done here. Okay? Now that my polynomial is in factored form, just like we did for quadratics, I'm going to apply the zero product property and set each of those factors equal to 0. And now I can solve each of those factors independently. So 3x plus 4 equals 0. I can subtract 4 from both sides and then divide by 3. For x minus 3 equals 0, I can add 3 to both sides. And for x plus 3 equals 0, I can subtract 3 from both sides. And I'm done. So this solving step isn't much, right? The main piece that we have to worry about is doing the factoring. Once we've got it factored, though, the solving is usually pretty easy. Everybody's okay with this idea? So let's look at 14. That one, the solving gets a little bit trickier, but not so much. So let's pretend that this was a solving problem that was equal to 0. I would do all the factoring steps exactly the same until I get to here. I'm then going to apply the zero product property and set each of these factors equal to 0. And then I'm going to solve each of these factors independently. So 2 of these factors are very easy to solve right away, right? X minus 2 equals 0, that's easy to solve. And 2x minus 1 is equal to 0. That's also really easy to solve. Any questions on those 2? No. Okay. So let's worry about then x squared plus 2x plus 4 equals 0. How do I solve something like that? You got an idea, Caden? Looks like you're thinking about something. Definitely can't do that. What kind of an equation is x squared plus 2x plus 4 equal to 0? It's a quadratic. So what are some of the ways we use to solve quadratics? We could try to factor this, okay. Are there 2 numbers that multiply to give us 4 and add to give us 2? Are they real numbers? Right? The only things that multiply to give us 4 are 1 and 4 and 2 and 2, or negative 1 and negative 4 and negative 2 and negative 2. None of those are going to add to give us positive 2, right? So we can't factor this, which is a bummer, but that's fine. How did we solve a quadratic that we couldn't factor? We use the quadratic formula. That's what we're going to use here. So the quadratic formula is x equals negative b plus or minus the square root b squared minus 4 times a times c all over 2 times a. So if I look at the part underneath the square root, I have 2 squared minus 4 times 1 times 4. 2 squared is 4. 4 times 1 times 4 is 16. 4 minus 16 is negative 12. How do I take the square root of a negative? What did we do back in chapter 3 when we ran into that? Well, not negative, but yes. So the square root of negative 12 is going to be I square root 12. Everybody remembers kind of doing that? Now, if you stopped here, that would be fine, but this would not be the answer that would like spit out of your calculator. We can do a bit better than this, because we can simplify the square root of 12. Remember that 12 is 4 times 3. Everybody's okay with that? So the square root of 12 is the square root of 4 times the square root of 3. And the square root of 4 is just 2. So I can simplify the square root 12 to be 2 square root 3. And now notice in the numerator, everything is being multiplied by 2. So if I divide by 2, I can reduce and get that as our best answer. I wouldn't have marked that wrong, though, either. Just FYI. All right. Let's look at the last piece then. 4x squared plus 2x plus 1 equals 0. How should I solve that equation? Oh, guys. Nobody? How would I solve that? What was that? Well, guess what? It's not going to factor. Because 4 times 1, two numbers that give us 4, and then add to give us 2, it's the same situation as the previous one, right? If I can't factor, I use the quadratic formula. And here's a little fact for you guys. If I look at these quadratic parts, both of them came from a sum or difference of 2 cubes, right? The quadratic part from the sum or difference of 2 cubes is never going to be factorable. Just FYI, you're always going to have to use the quadratic formula on that piece. Just so you know. Because you're going to get an imaginary solution every single time. They all will have i's in them as well. That's also probably worth making an observation of. Okay, so if I look at this thing, look at the numerator. Oops, it's times 4 still down there. Isn't that exactly the same thing as the other quadratic that we had to solve? So I'm not going to write out any of the simplification. I'm just going to go all the way to this. Oops. Everybody's okay with me doing that? It's the same simplification as the other one was. All right. Notice the numerator, everything is being multiplied by 2, and the denominator is also divisible by 2, so I can reduce that. And there's my best answer. Okay? So these solving problems, not decidedly different than what you did last night, right? The bulk of the work is getting it into the factored form. Once you're in the factored form, you just set the factors equal to 0 and solve them independently. Worst case scenario, you might have a quadratic factor that you have to use the quadratic formula on, or use some of the other quadratic solving techniques that we developed in Chapter 3. But that's kind of the worst they'll get. Okay? This is why when we took the Chapter 3 test, and some of us had a hard time with this, I offered the redo part and made you guys come and show me what you had retaught yourself before you took the retake, because this solving of a quadratic skill comes up over and over and over again in this semester. It is the single most important solving techniques that we can have for during this course, because they're used throughout. Okay, well, let's stop here.